You write a simple API endpoint and test it locally with 50 dummy users. The database responds in 15 milliseconds, and everything feels perfectly responsive. Then you deploy to production. As your user base scales to 100,000 records, the environment changes. Your server CPU pegs at 99%. Individual requests drag out to 5 seconds, and the database begins to time out. The code is functionally correct, and it worked on a small scale. We need to understand why increasing the data volume breaks a system that was previously stable. Functional code is not always production-ready code. Operations that execute instantly in local memory become massive physical bottlenecks when applied to a large-scale database. When an endpoint fails under load, the programming language is rarely the culprit. Performance limits are usually reached long before the logic is executed. This execution waterfall chart maps a single 5.4-second request. The vast majority of this time is consumed by unoptimized network, disk, and memory transfers. Optimization starts by deconstructing the timeline and stripping away these specific blocks of wasted time. We are going to deconstruct 5 specific coding mistakes that generate this bloat and reduce that 5-second execution time down to just 14 milliseconds. Database optimization is the practice of managing the physical cost of data retrieval across hardware boundaries. The first optimization boundary is the network. The most common performance killer here is the N+1 query problem. Consider a scenario where you fetch 100 blog posts and need to display the author's name next to each one. A common mistake begins with one initial query to fetch the list of 100 posts. The application then begins looping over each post, firing off a new query to fetch the user record for that specific author ID. By fetching 100 posts, the server just sent 101 separate round-trip queries to the database. At a scale of 1,000 posts, that becomes 1,001 separate queries. Network latency explodes because the physical time it takes for data packets to travel back and forth is multiplied by every item in your list. You fix this by using SQL joins or by fetching relational data in a single batch using the in operator. This consolidates the fragmented requests into one single query, bypassing the latency multiplier entirely. The N+1 problem occurs when a server treats a high-latency network connection as if it were a low-latency local memory loop. The second domain is disk I/O, specifically the cost of searching through unindexed columns. When you search for a value without an index, the database engine performs a sequential scan, also known as a full table scan. In a sequential scan, the engine literally opens row 1, checks it, then opens row 2 and checks it, continuing until it finds a match. If your database has 1 million rows, a single search forces the server to read 1 million entries off the physical disk and into memory. You solve this by adding an index to any column frequently used in where clauses, join conditions, or order by sorting. An index creates a separate data structure called a B-tree. This structure allows the database engine to traverse data logically. It follows the branches and bypasses nearly all the nodes to find the target value instantly. Searching 1 million rows drops from 1 million physical disk reads to roughly 20 logical comparisons. Indexing transforms a brute force physical search into a surgical memory lookup. Our third boundary is memory. Performance often suffers when developers use select star to fetch every column in a table. Imagine building a dashboard that only displays a username and a profile photo. Querying the entire user record to get those two fields creates a 5 megabyte JSON payload, especially if the table includes heavy binary data or long text fields. This wastes database disk I/O, saturates your network bandwidth, and consumes server RAM to deserialize the large payload. The fix is to explicitly declare only the specific fields required by your logic or your UI. By selecting only the ID, username, and photo URL, you drop the transfer size from megabytes to kilobytes. Fetching unused data starves the server's memory and chokes the network layer before the response ever reaches the user. Object relational mappers create an abstraction that simplifies development, but they frequently mask the physical reality of the database. While ORMs improve velocity, they encourage developers to treat the database as a simple local object store. This split screen shows the danger. Elegant ORM code on the left can generate a sprawling monstrosity of inefficient joins and nested subqueries on the right. To see through this extraction, use the explain analyze command available in PostgreSQL and MySQL. Prefixing any slow query with this command forces the database to reveal its exact execution plan. The execution plan shows exactly how many milliseconds were spent sorting and whether the engine used an index scan or a sequential scan. Always enable query logging on your ORM during development to maintain visibility over the raw SQL it generates. Effective backend engineering requires verifying the physical execution plan that exists beneath your code abstractions. Effective optimization requires treating the database as a distinct, resource-constrained environment, rather than a simple extension of local memory. Local tests often hide performance issues that only emerge when the volume of data exposes inefficient retrieval patterns. At the network layer, eliminate N+1 queries through strict batching and proper joins. To protect your disk and memory, use B-tree indexes and strictly limit your data payloads. This summary matrix maps the necessary audits for any system. Validate your network batching, verify your disk indexing, and target your memory selects using Explain Analyze. Apply these profiling methods to your current database architecture, whether using Postgres, MySQL, or MongoDB. Ultimately, high-performance systems are built by developers who understand and strictly control the physical boundaries that data must cross.